Hello, everyone. Welcome to our session this morning. We're just a few minutes ahead of the start time, so for those of you who have dialed in already, thank you for waiting patiently for just a few more minutes until we officially start.
Good. And Dita, you can see my screen still?
Udi, hang on. Let's use the chat function here. Hello, everybody. We were just giving a few more people a chance to dial in. Welcome to our webinar today. Thank you for your interest in attending. We have a full agenda for just about an hour, so just a few quick notes before we get started. We have a big group today, so attendees will be in listen-only mode. However, you'll have a chance to pose questions with the question chat box. Please indicate if there's someone specific who you'd like to address your question to, and we'll do our best to ensure that they get to your question. We are going to hold all questions until the Q&A at the end, and we'll answer as many as possible. And if there's any that don't get answered, we'll be sure to follow up by email with any that did not get addressed. We've also uploaded today's presentation to the platform, so you can refer back to it later and contact us with further questions. And on that, I will let Bruce start with the introductions.
Good morning, everyone, and welcome. I'm Bruce Baxter, Senior Vice President of Operations at Cooper General Electric, of which I manage our modular data center division.
Good morning, everybody. My name is Udi Paret. I'm the Zuta-Core President residing in our U.S. headquarters in California.
Good morning, everyone. My name is Matt Kokel. I'm a principal and market leader in Affiliated Engineers Mission Critical Practice.
Yes, and this is Daniel, Daniel Bizo. I'm a data center analyst with 451 Research in London. Thanks for joining. Yep, so thank you, Nandita. So my role today, so I'll kick it off, the presentation today. And my role is to paint you a backdrop with, broad brush strokes, for the topic of liquid cooling. So I hope I will manage to show you new angles and a new narrative around liquid cooling that's going to tell you something new and not just repeat what you probably already know about liquid cooling and generally the topic. So next slide, please. So the title of my section is Now is the Time for Liquid Cooling, and I will shortly explain, my line of thinking, our line of thinking, why we at 451 are of that view. Next slide, please. So just a quick few words about 451 in case you don't know us. We are a technology market analyst firm with a focus on the change in IT, and especially we've got a strong focus on the data center stack, all the way from from physical infrastructure all the way to cloud services and applications and AI. You will notice that Uptime Institute is part of our group. So, I'm fairly certain most of you know the name. So they are the consulting firm that developed the tiering system. And that's a great benefit for us because we can work closely with them and they give us access to, data center operators and consultants for our research, which is great, for reality checks, really. So we are not getting carried away with technology. Next slide, please. This is an example of our research which we did 2 years ago. The graphics shows you selected technologies which we view potentially disruptive to the data center stack. And what you see on the chart is a sort of ranking of the select technologies by a panel of analysts and data center industry professionals. And essentially, to simply read it, the more you are towards the upper right corner of the chart, the more likely and faster people expect that technology to penetrate the data center, and also the size of the bubble shows you the size of the impact. So again, I must reiterate that it was done 2 years ago, and you can see direct liquid cooling is there. Actually, we started tracking and covering liquid cooling way before that, probably around 8-9 years ago now. And I certainly believe that should we run the same questions, the same survey against the panelists today, I think liquid cooling would markedly move to the upper right direction. And this brings me to the topic or title today. Why now? Why now is the time? I'm going to in a few minutes detail the 3 major reasons I want to share with you that we believe are relatively new. So these are factors that I believe have become stronger, grown markedly stronger in their effect. So first, air cooling. Next slide, please. So air cooling, it reads maxed out. Why is that? So we've seen, terrible PUEs 10 years ago in the industry, and over the last 10 years or past 10 years, the industry has really come a long way in improving its efficiencies, and we brought down PUE levels according to our surveys from the above 2 to well under 2, and now it's approaching 1.5 on average. So that means that there are some operators in meaningful numbers that are already well below the 1.5 threshold. At the same time, you have to sort of, face the fact, we all have to face the fact that there's only so much we can achieve with air cooling. And ultimately, simply because it has become so much better optimized and so efficient. That means that further efforts that goes into optimization will bring only marginal gains. And even if I look at the most aggressively optimized facilities, air-cooled facilities, we are looking at PUEs of 1.15 maybe in moderate climates such as London, to 1.2, 1.3 depending again on climate, on location, and choices of technology and also operational regimes. What's the temperature band people are willing to put up with? To go beyond that, we would need to see much more aggressive behavior when it comes to ASHRAE envelopes. So we would need to see the adoption and excursion into ASHRAE allowable ranges. So temperatures beyond 27 degrees Celsius, so centigrade, and that generally speaking, although physically and technically it should be possible, simply because it also opens up lower temperature bands to buy back lost life cycle time. But essentially the bottom line is we don't really see that happening because it suddenly becomes not really acceptable for commercial or business case reasons, and that really puts a hard limit, if you like, to what air cooling can achieve in terms of efficiencies. And the same goes for the capital cost savings. So if we charted how the costs of facility and cooling has come down over the years, it would show a similar trajectory. And again, the story is here that air cooling is now highly optimized, and in order to make further gains and escape this plateau of lacking efficiency gains, you need a step change, you need a shift. Next slide, please. The other big factor is server power and chip power. What you can see on this plot chart is entries from the database of the Standard Performance Evaluation Corporation, which is a non-profit industry body that develops computing benchmarks. And essentially, this is one of the benchmarks that measures power efficiency, and these are readings how much power systems under test burn when under full load. And what you can see is that over time, the plot chart clearly shows an increase of server power when we are thinking about servers that are even those servers that are optimized for efficiency, they are becoming more powerful. So this is not just an arbitrary trend where you gain more performance for more power. This is really servers people think, or vendors at least think, are power efficient on the infrastructure level. And again, we have gone from 200-300 watt domains for most systems that are efficiency optimized to 400-500 watts. So that already tells you tells you a lot about the direction of travel. But really what really makes this call and this webinar today timely is that Intel just released their latest generation of server platform. And actually, they opened up the power allowance for processors to 400 watts. So that's actually double the level of what was acceptable in the past, which was around 200 watt thermal power. Now it's 400 watt thermal power. That means that we're soon going to see servers that burn 600-700 watts in one rack unit space. The real takeaway here is not even this density of the server, but the thermal density of the chip. So if you think about 300-400 watt processors under a heavy load, that's already something that will be problematic and difficult to cool with air, simply on account of the volume and velocity of air you would need to move through the servers. Next slide, please. And of course, there is the question of high density cabinets. It must be said that average densities we've seen fairly flat, going moderately up in recent years. But what's changed and what's new is that most facilities these days report on having high density cabinets above 10 kilowatts. Actually, almost half of them, plus 40% plus of them, have cabinets that are over 20 kilowatts. So that also tells you that it's going to be increasingly common to have those high density cabinets in your facility or in the facility of your partners and customers, which also, again, pushes the case for liquid cooling. Next slide, please. And the third big topic is climate. So climate can be, many things. The first angle of climate is the operational efficiency of the facility. In the past, we were fortunate enough to have the biggest data center locations such as North Virginia, London area, Frankfurt, in fairly moderate climate. So nothing terribly extreme in terms of temperatures and humidity. Going forward, as the data center industry expands and builds up capacity in more and more locations driven by cloud buildups, and also as enterprises want to consolidate increasingly in co-location facilities, that means purpose-built data centers again in more metros. This balance will shift to locations where climatic conditions are not really ideal to drive aggressive PUEs with air. So liquid cooling there is a response. The other consideration, next slide please, is climate change itself. Yeah, so thank you. So climate change. So again, according to our surveys, climate change is becoming a top of mind consideration when people are looking at their data center design and the resilience of that data center. And what worries increasingly, many people, is that in the future we might see extreme weather events that simply have not seen and observed in the past, breaking the engineering assumptions around temperature and humidity, wet bulb conditions and such. And again, liquid cooling, I think there's a strong case to be made here for the use of liquid cooling, because that makes the operation largely climatically agnostic. Next slide, please. And then there is, of course, the question of sustainability. One factor to consider here is that the commonly used refrigerants and compressors, refrigerant 134A, is actually being phased down already aggressively in the European Union, and we also see some of the markets, including the US, to follow suit, in a not too distant future. That means that actually the supply is going to dry up on account of regulatory squeeze, which means the prices will escalate. But over time, more importantly, it will not be possible to simply source enough refrigerants to keep all the chillers and compressors operational today. So the change to alternative, on the other hand, will mean potentially the loss of performance for existing sites, and especially for future sites. That means that potentially relatively bigger mechanical units, bigger chillers, bigger air conditioning units to drive the same amount of cooling capacity. Again, the message here is that for both operational sustainability and also for environmental sustainability, as a green message for corporate responsibility, liquid cooling offers a way out of this squeeze. And yeah, that brings me to the summary of my section. Next slide, please, which is liquid cooling, simply put, allows the data center industry to carry on reducing cost and increase efficiency gains well beyond of what's possible with air. It extracts all the performance from silicon, and it is climatically agnostic and helps operators achieve resilience and sustainability. And with that, thank you very much for your attention, and I turn it over to Udi, who is going to discuss what Zuta-Core can offer.
Daniel, thank you very much. Indeed, quite remarkable timing, I would say. Interestingly enough, the Zuta-Core team that founded the company back in 2016 in Israel had both the same vision and similar realization. They understood that harnessing two-phase change phenomenon for cooling would merit by far the most efficient way of cooling. They also realized that though it's not enough just to use the two-phase change. By that time, there were quite a few major projects trying to implement two-phase change, including some Fortune 500 companies and national labs that actually failed to do it. It required, or they did do it, but required high-pressure systems, very expensive, not scalable. In the process, they were sinking tens of millions of dollars. So it did require some breakthroughs in implementation in order to realize it into a scalable system. One that would really deliver this very unique combination that it would be a two-phase change, low pressure, direct on chip, on demand, using non-conductive refrigerant. So how does it work? The magic really starts with our special heating, the evaporator. We call it an enhanced nucleation evaporator. In short, ENEs, we'll refer to it as ENEs. For those of us who are familiar with single-phase based cooling, such as direct-on-chip water cooling, that is using the physics of what's called specific heat. Therefore, it is solely dependent on flow rates. The more heat, the higher the flow rate needs to be. In contrast, in Zuta-Core case, we are leveraging a completely different physical phenomena using the latent heat in the virtue of the evaporation of the two-phase change from liquid to gas. And therefore, we are really independent of the amount of heat coming under the evaporator. Think about boiling a pot of water. Independent of the amount of heat you'd put underneath, the water would continue to boil at a standard, at a constant temperature. So that means that it's not just safe in terms of not using water and therefore alleviating the risk of IT meltdown. It is significantly more efficient cooling that scales well with higher wattage devices while keeping the cooling system in that very same small form factor, which again translates to scalability. Just to burn the ear a bit about the key differences in the physics that really are the essence of it. If you look at the table, it's jumping out that really on both on the mass flow, on the lowest delta T, which essentially is the critical factor that allows the efficiency, coupled by the low mass flow that is required, that translate into a much lower, in order of magnitude lower flow rate, and in our case, flow rate that only happens at maximum power, is in the core of the technology. So when you look at the system, when you look at the bottom right-hand side, every one of those ENEs, those evaporators, is in direct contact with the chip. It holds in it a very small pool of non-dielectric refrigerant. We're currently using the 3M's Novex 7000, sitting ready for when heat is generated. That means that it translates into two of the system's key benefits. It's instantaneous and it's on demand. Furthermore, all the devices are connected in parallel, and that translates into two other key benefits. One is scalability and the other is system efficiency. Just imagine that each heat-generating device gets cooling only when it needs it instantly, irrespective if one chip is idle or the other is running in turbo mode, or all of them are constantly overclocked. So all devices are kept at the same constant temperature, irrespective of the ambient temperature and at the low pressure. When you look at the system components, from left to right, we have three basic sub-assemblies, hardware sub-assemblies. On the very left, you're looking at the server implementation. Those are the ENEs retrofitted with liquid coming in and gas coming out. In the next to left, you'd see it's just one implementation into a rack level. This is the the refrigerant distribution unit. And to its right, a photo of a heat rejection unit, in this case, an air-based heat rejection unit, then outside unit. We do have similar products for an in-rack, single in-rack product. All of those are coming with a platform of software that really does the monitoring and management of the system, although the system is self-regulated. So the platform allows us over time to build more feature and functionality around software-defined cooling. So combined, you're looking at really one of the most efficient direct on-chip cooling technology that provides on a system level a constant PUE of 1.03, again, irrespective of whether it's in Abu Dhabi or in London. And therefore, with the shrinkage of equipment in footprint and a much higher density, would typically translate to a significantly lower CapEx and lower OpEx. The delivery of that is done with and through infrastructure partners of ours, which would be a great opportunity to hand it over to my good friend and partner, Bruce Baxter at Cupertino Electric Inc.
Thank you very much, Udi, and welcome everybody, and thank you very much for joining. Udi, if I could have the next slide, please. So I'm assuming many of you are wondering why an electrical contractor is involved with this webinar, and just a little bit of history. We started a modular division back in 2010 primarily to reduce labor risk on projects and to increase overall quality of the data center builds at that point in time. As a net result, as we grew, we continued to offer more and more products, one of which was cooling solutions. And as a result of that, we got ourselves in a position of when we got above 13 kW per rack in our modular solutions, it created more and more problems in terms of how we're going to handle the air. And that led us to a discussion with Udi and Zuta-Core team about some other possibilities, and that's when we joined the team as a partner to further develop the cooling solution and to provide integration. Udi, I think we need the slide deck back up. Thank you. Net result as of today, we're at about 750,000 square feet of manufacturing, produce 3-5 modules a day, about 1.2 gigawatt installed, and we offer turnkey modular data centers, data center components, fluid cooling solutions, and energy storage solutions as well. Can I have the next slide, Udi? So the net result was, what do we want to fix? What was the problem set? Ultimately, we wanted to ship fewer square feet. So if we were able to eliminate ductwork, hot aisle, cold aisle containment, have the flexibility to change the configuration of the racks and readjust the utilities, overhead, network, and power distribution, it really was a benefit to us. We want to refine and simplify the cooling system. Udi's point about direct on-chip, on-demand, and instantaneous on-demand of the cooling without any control points was, again, very attractive to us. We're able to increase the rack power density, make more use of stranded power in brownfield installations, significantly lower the maintenance of our modular data centers, lower PUE, and increase flexibility of the cooling system. Another really attractive thing for us was to utilize a proven, repeatable design. So regardless of the climate in which we're installing modular data centers, we were able to have a proven design that will work in 95% of the locations we go to. One thing that's interesting, if you look at the picture on the right, can you go back, Udi, please? if you can look at the picture on the right, this is an example of ship in square footage. Is that there's 3 indirect evaporative cooling units supplying that white building, which is an modular edge data center. And the square footage of the evap units is about 2,000 square feet, and the square footage of the modular data center is about 1,400 square feet. So significant reduction of overall footprint and complexity of the system. Next slide, please, Judy. So the advantages of Zuta-Core is, as I already mentioned, is the reduction of square feet, the elegance of the design with the chip direct control, the capabilities of up to 50 kW per rack, and then the brownfield insertion for capturing stranded power, which is important to us from a perspective of a number of clients have older data centers in which the HVAC systems are at max, but yet they have stranded power and they want to increase capacity in those existing data centers. They want to do so without significant capital costs or continuing at the current PUE levels. The solution offers us a great opportunity in terms of being able to increase capacity and make use of the stranded power without impacting the current HVAC system, and all the while be able to do that in a live data center with a seamless transition. One thing that was very, very attractive to us. Reduction of moving parts, maintenance and PUE and control points, and the increased flexibility over current designs. Us having the ability not to have hot and cold aisle containment in our modular data centers, even in traditional builds, to make those types of solutions go away, and at the same time, elimination of ductwork or RTUs in the data center space was very attractive to us. So one thing that I thought might be important is how to engage. What would the next steps be if you're considering a solution like this? One thing that we think is important is to work to a pilot solution of 50 to 250 kW in your facility. Gives us an opportunity to analyze cost, performance, and operational benefits for your model. We can define production design criteria for cutting into any plan of record, which we think is an important step because it allows us, through the pilot solution, to start to look at that POR. So there's a timely insertion if it's a requirement or if it's something you desire. And then the engineer, procure, and construct EPC of the installation and commissioning. The important thing for us is that it gives us a very flexible solution with a proven technology and the ability to ship fewer square foot. Really important. With that, I will hand it over to Matt at AEI.
Thanks, Bruce. Thanks, everybody, for attending the meeting. Today, I want to talk about how we can efficiently cool very dense computer environments. As we all know, there's kind of the traditional design, as you can see on the screen here, where you've got some type of hot aisle, cold aisle type of environment, and maybe a ceiling plenum where the hot air returns back. Very, very traditional type of design. And as Bruce was kind of talking about, trying to eliminate, some of the inefficiencies relative to having air mixing into the environment and having to worry about containment. Can you go back to the previous slide, please? Yeah, the one thing that we always have to evaluate is how much heat is being generated right directly at the rack and at the server level itself. And some of the phenomena of having recirculation of air and airflow management issues really kind of impacts how the data center is cooled. And that's where the advantageous principle of having some form of containment comes into play. Next slide. So as we see, many data centers have cooling towers, chillers, pumps, crack or craw units that are sitting around the perimeter of it. And we're seeing the density kind of grow from the typical average of 3.5 to 5 all the way up to 10, as Daniel was kind of talking about in his portion of this presentation. And again, this is kind of just its medium density, kind of baseline, if you will, from a data center environment. Next slide. While we talk about the kind of traditional data center design, we'd like to also focus on the more efficient data center design, where maybe there's an evaporative cooling depending upon the climate. Again, the use of some form of hot aisle containment, and just delivering the air directly to the space to try and allow the servers to pull that air in. Again, looking at a pretty efficient type of data center here, where again using some type of indirect evap or direct evap to allow a compressorless type of data center cooling system. Next slide. And again, maybe even more efficient might be the removal of any type of water, where we're just taking direct outside air into the environment using some form of containment. And maybe if we have higher density loads, there's some form of in-row cooling type of solution to help supplement the overall supplied air from the outside and from a large air handler. Again, maybe this is a little bit more efficient, kind of depends upon your locale and the control systems that are implemented as part of this type of solution. Next slide. And again, maybe even more efficient is just that almost data center that's set directly outside, right? 100% direct air coming directly into the space. Maybe there's some form of containment, and again, just trying to directly exhaust that air right out of the space. So once through air in this type of application, maybe even more efficient. Again, the only thing that you're having to use from an energy perspective is some fan power to move the air across a damper or across a grill to get it into the space, and then maybe another fan to exhaust it as well. Next slide. And then with some of the higher density requirements that, as Daniel was kind of talking about previously, and as we're seeing in the marketplace today, the use of almost kind of point level cooling at the rear door of a cabinet, whether that's water or refrigerant or CO2, there's various different means and methods and systems out there that can provide this type of direct, rear door heat exchange type of environment. But the thing about this is we're all still moving air. Every one of these scenarios, as shown, is still moving air across a heat sink internal to the IT equipment, which, the question starts becoming, when do we reach a density that we can't do that? And again, if we start increasing that supply air, instead of maybe 70 degrees F in this example, it increases to 80 or 90 degrees, depending upon a person's comfortability with the recommendations from ASHRAE. All right, next slide. So to that same point, what happens when air is no longer enough? What happens when it's no longer enough to cool the chip density and be able to move enough air across the heat sink to provide that cooling? Next slide. So what's driving this density? What's driving the higher density computing trends? So we see it all in the news. Everybody is probably connected to LinkedIn or some other type of media outlet that we can see, artificial intelligence and or machine learning, augmented reality, virtual reality, real-time imaging. As we start seeing more and more driverless cars out there, that's going to be a very large part of that capability. For many organizations that are out there looking to try and mine data to maybe more efficiently deliver packages to people, maybe looking at data that or images of products sitting on a shelf to better understand trends of buying, this finding the needle in the farm of hay type of idea of really deep data mining. And then obviously pattern recognition and predictive analytics are additional items that are really driving this computing density, the ability to process data much faster, to process much more data than we've ever had to process in the past. So how do we accomplish this? Well, we're seeing chips, as Daniel had kind of talked about before, approaching this 4, 5, and maybe even 600 watts for this thermal design point or the thermal design power of a chip. So this is, again, some of the newest chips from Intel, their gold and platinum CPUs in their lineup. And then again, we can't forget the GPUs that are coming from NVIDIA and others out there, approaching 300 watts and more. Again, this is the public data that's coming right off of websites for both NVIDIA and Intel, and it's showing that we're really starting to approach these much higher densities from a chip standpoint. And I'm not sure how many people saw this article come out relatively recently about Google also moving towards liquid cooling because there are machine learning chips that are out there. So the question is not what we know now, but what is coming. And that's everybody's crystal ball, right? So what we know now is that chips are increasing in power density, they're getting hotter, and the computing density is obviously getting much greater. So this is a kind of an interesting graphic that I was able to find while doing some research on NVIDIA. Is you can really get the sense of taking the CPU only type of servers and really crunching that down to maybe just one GPU type based server. Again, application dependent, everybody has different needs, but again, we're talking about the densification of computing platforms in this case. Next. Well, not only computing platforms can get more dense, but also the data center can get more dense. This is just a little bit of a graphic, an example of taking that baseline condition that we talked about previously and increasing the rack densities from 8.6 to 17.2 kW per rack. And again, in this case, we're showing the Zuta-Core water-cooled heat rejection unit tied to an existing chiller plant in an existing type of facility. So the retrofit options are kind of endless in this case, because if we have an existing chiller plant or some type of source water cooling, we can leverage that existing asset without having to remove it. And again, maybe we just don't need as many of those assets to provide the cooling that's needed in this case. Next slide. And further to that, maybe we do want to continue to leverage the existing space that's available, and we can use, again, increased density, and we can also gain further efficiency in that existing type of facility without having to do much of anything other than adding additional Zuta-Core to the existing infrastructure. Next slide. So let's go down a path of a use case here. So we're going to consider a new build type of data center. Again, the graphic is a little exaggerated, but done to kind of make a point here. So this baseline data center of about 500 kW is operating with an overall facility load of about 670 kW worth of power. PUE right in the kind of midpoint that we see in the market these days, about 1.2. Again, new build, so I can do a few things differently for this kind of traditional design. And an overall rack density of around 5.4 kW of capacity here. Next slide. So what happens if we want to increase that capacity of our kind of baseline new build type of scenario? So again, we're looking at potentially increasing the square footage, increasing IT load. Again, we went from about 500 kW to now a megawatt. Obviously our facility load is increased. Our PUE may have stayed about the same. Again, we're just kind of increasing the overall IT load, and also the density per rack has stayed about the same. And we're kind of seeing this ROI for this type of application maybe in the 3 to 4 year range. Next slide. But what happens when you build it with Zuta-Core? And I guess kind of one of the things that I'm excited about is how simplified this becomes with Zuta-Core and the ability to deploy a chip level cooling solution. This case is we've decreased the overall square footage, much to Bruce's point earlier. We've increased the density, so I'm at 1.2 megawatts worth of capacity. The facility load is right in the same point as the previous builds. The PUE is much lower. We're down to 1.05, and we're under a year from an ROI perspective to accommodate this higher density. And again, we're accommodating this with a 50 kW per rack in this application. Next slide. And it's just kind of a summary of this. You can see here, what our base metrics are versus our, scenario. Again, the baseline, 1.24, kind of keeping that consistent to 1.24 for the air-cooled. Even if we go to a direct-to-chip liquid cooling solution, we're not still getting quite the same level of capacity or of efficiency as we can with Zuta-Core. Again, because I may have to hold that water temperature a little bit higher depending upon the chip and chip temperature. So again, we're really gaining some higher efficiency as well as a lower OpEx, as well as a higher return on investment or a lower, quicker return on our investment. The next slide. And with that, we'll turn it over to questions and comments at this point.
So for everyone who is attending, if you do have any questions, please feel free to use the question chat function, and as they come in, we will address them. Sounds like some of the audio might be having issues, but Matt, it looks like someone would like you to elaborate on the last slide, please, especially the CapEx and OpEx.
Sure, could we go back to the last slide? So the CapEx and OpEx in this case are really looking at the mechanical portions of this without getting too far into the electrical. Again, we're kind of talking about the value from a new build baseline perspective versus implementation with Zuta-Core. We would anticipate that there would be considerable decreases also in the electrical, which are not captured as part of the OpEx and CapEx in this model. Our values on how we're calculating the OpEx on an annual basis is basically looking at our baseline scenario to provide this in a relative standpoint. So we see that with a air-cooled based type of cooling solution, we're seeing a higher OpEx cost, which we would anticipate as there's many more moving parts, there's many more components that are required to support an air-cooled type of solution. With Zuta-Core, obviously the OpEx cost in this case is much lower because we're only doing heat rejection directly at the chip. There's very, very small pumps that are required to support the movement of the refrigerants around. The CapEx, is, in this case, is a little bit lower, and we're anticipating lower than the direct-to-chip liquid cooling solution based upon our current analysis in this case. And that's the reason why we've represented that as such in this scenario, in this kind of overall summary. And then again, from a PUE standpoint, we're anticipating that the PUE for a facility in this case is much lower than anything else from either water or air cooled. Again, because we have such small pumps that are having to move that liquid refrigerant directly to the chip in this case.
Great, thank you, Mark. So I'm back. Sorry about that. I had some issues with my audio. So yeah, there's another good question on about the applicability of the Zuta-Core techniques or technology to servers. So the question is, do you need specific servers, or is it universal? And also, what happens to the warranty? So maybe this is for Rudy.
Yeah, can you hear me, Denan?
Yep, loud and clear.
Yeah, thanks for fitting the question. So a couple of things with regard to the server. I think there's also a question regarding the rest of the heat generating components there. So one of the benefits of this technology is that it is a very simple and straightforward retrofit of any server. We've experienced with quite a number of different servers at different densities. Literally, as our customers actually timed us, once the server is determined, the actual retrofit process takes literally 4 minutes. That is to open, including opening the server, taking out the existing heat sinks, putting in the new E&Es, our evaporators, closing it down, and testing it. So this is a very straightforward process that can be done by the server owners or the IT configurators, which leads me to the next question, and that is about server warranty. So eventually, server manufacturers, we're in discussions of number of them, got to a point today that they are providing direct on chip water cooling solutions with their own SKUs. Although, as everybody knows, the IT meltdown risk exists, so that it's a good evidence of the pain point. We are in discussions with a number of them to do the same with ours. Until then, we have announced just about a month ago the first one, and there's an upcoming announcement of the next two system integrators that their business is server configurations per requirements, and they do provide already here in the States warranted retrofitted servers with our E&Es. So from a server warranty point of view, the base is covered. Last but not least is a question about the server on covering the heat generated on a server basis. It is more typical than not that 70, in some more dense servers up to 80, and as we saw with the upwards of now chips going upwards of 400, that about 70 and above of the server heat is generated from the CPUs and GPUs. So about 20 to 30% is what's left for the fans to take care of. Having said that, it's very typical that the rest of the components on the board do not require that level of ambient temperature on the board as the CPUs and GPUs required, and therefore, if you account for higher temperature there, what happens is that the fan power is reduced to about 5 to 10% of what it would be without the direct-on-chip evaporators. And that still require some level of air cooling as well.
That's great. So there's also a question about the pressure for the refrigerant, and I think Matthew signaled you might want to answer that.
Yeah, the system operates with very, very low pressure. In this case, I can respond to the person specifically about the specific pressures. But yeah, it's very low pressure, very small pumps. Again, that's the reason why we're getting. That's the reason why the system operates with such low energy usage, is because there's very, very small pumps as well as very small pressure in this case.
Okay, and another question is about facility scale deployment. So I guess the question is, have we've got an example, a reference deployment, or maybe an engineering exercise that shows how a full-blown facility would integrate this? Maybe this is to Bruce. Yeah.
Let me take a stab at it. This is Udi speaking. Thank you again for the question. We have deployed engineering systems both internally as well as with partners. You mentioned CI. That's a good example of a system that was deployed there, as well as taking those systems into third-party testing, including last year's very extensive environmental test concluded successfully at the NTS lab in California. As far as data center environment deployments, we are eyeing the first deployments in data center environment actually this quarter. So starting this quarter, you would see first deployments in data centers.
Okay, great. And why have you? So there's also a question about the availability. So is Zuta-Core technology GA and in production? And you know, what's up with pricing? How do you go about that?
So it is indeed in GA. As I alluded to before, and that's a good segue for Bruce to discuss it as well. We are working with our infrastructure partners. They are the ones who actually front end and provide the complete services, engineering through commissioning, and that is available. So Bruce, maybe you want to add to that?
Sure. So in terms of the components related to the Zuta-Core solution, we currently have a developed manufacturing supply chain support that system, and we're prepared to be producing. I believe the plan was up to 10 megawatts a quarter, beginning the end of the second quarter this year. So it's scaling really nicely. If we look back to how to engage, you know, our preference obviously is to put a pilot in first so that we fully understand what the client is looking for, and then go to a production solution.
Thank you. We've also got a question on the sort of resiliency of it. So from Tom asks, what happens because the chip is covered by a single cold plate, if you like, and what happens when the delivery of the fluid fails? What's your take on that? I mean, this is open to the floor. I'm sure who wants to take the lead.
Let me take again a step here, and maybe you can chime in later with some more. But a few things. One, just to make sure, although it's kind of maybe implicit in the question, but one of the key differences here is that because we're using the 3M dielectric, non-conductive, safe green refrigerant, unlike water. We have alleviated the IT meltdown risk altogether. So even if, God forbid, there's a spill, there's no IT meltdown risk at all. In fact, this refrigerant was developed originally to clean electronics. So that's an important point, just to highlight that. Now we have several, on top of that, we do have several leakage detection and protection levels in both in the hardware as well as in software, just to make sure that we can identify any such issue if and when it happens, which leads me to answer the question directly. If there is a disconnect to a certain chip, that chip, of course, just like it would happen with an existing heatsink or problem there on a fence, that heatsink would go into a shutdown. But the whole system is, of course, parallel and therefore would be typically compensated by other CPUs in the system.
Anything to add, Matt? Yeah, go ahead.
Yeah, I think you hit the nail on the head in the last kind of comments there. A chip is naturally going to protect itself from thermal overload. That's especially with some of the newer chips and the newer cooling newer technologies associated with the chips. They're going to throttle their speed back. They're not producing as much heat. I think the other kind of great part of this is looking at how Zuta-Core delivers their solutions. There's a lot of redundancy and resiliency built into the solution naturally with redundant pumps, really high-end controls, so that there's a value of redundancy naturally built into the system. When you look at the way that the system operates, you're basically having a pool of refrigerant that's sitting there at the chip, essentially boiling off. So you would have to have a really pretty major failure to not have cooling at that chip. And just the simplicity and nature of this, it's yes, we have a couple of moving parts more than just a passive heat sink, but the value and benefit that you're getting out of having this is, I think, far outweighs the bad side of that.
No, that's great stuff. So one last for Bruce. So there's a question on stranded power. You made the point that you can capture, recover stranded power. So can you maybe expand on that in 2 minutes? Like what exactly you meant and how Zuta-Core's approach is ideal for that?
Yeah, as I briefly mentioned earlier, is that in many of the older data centers in which they want to increase capacity and they have the power capable to do that, the ability to go in with the Zuta-Core cooling solution and not impact the current HVAC system is really important to us and to our clients. The result is they're able to capture the stranded power, increase the capacity of the data center, and lower their PUE all in one solution that can be. This is what I believe is key. It can be done seamlessly. It can be done in a live data center without disrupting the current HVAC system. And we think that that's very, very important.
Okay, so we just had a last minute question coming in on tier 4 and continuous cooling. Probably that requires a little bit response, but any thoughts on that? Matt, maybe how you can deliver like something that's tier 4 certifiable, continuous cooling. Is that something you've looked at?
We look at this as solving the problem of how do I deliver cooling for very high density applications? And I think that the industry is going to struggle with that, specific tier 4 guidance. I think how we like to look at problems from an engineering perspective is maybe something that is guiding the process versus following it maybe to a specific. And maybe Daniel, you can speak a little bit more to that. But I think that in this case, we're talking about trying to achieve very high density solutions directly at the chip. And I don't know if when the tier 4 redundancy levels were developed that they really had a lot of direct to chip cooling solutions in mind as part of the guidance relative to tier 4. So maybe that's something as the Uptime Institute looks further at direct to chip liquid cooling, that there will be some revised guidance relative to the tier levels when it comes to that type of scenario.
And just to add to that, Daniel, maybe just 10 more seconds, just to build on that. I alluded to some upcoming data center environment deployments, one of which is going to take place with the participation of the Uptime Institute, exactly to do what Matthew just described.
Okay, no, that's good news. I mean, all I can add, I mean, I'm not an uptime engineer, but all I can add that uptime, design rules, if you like, are agnostic to the technology. So the question is always, how you can feed that piece of, technology into that framework of continuous cooling requirement and fault tolerance. And of course, there's always the question which could be up for debate from my experience, that what is a maintained piece of component, and what can be viewed as something that you don't have to maintain. So, but that it's a longer conversation, and I want to be respectful of everyone's time. So, thank you very much, gentlemen and Anita, and thank you very much for all of you for attending. And in conclusion, maybe I might just add that in summary, we think that liquid cooling is something everyone should look at. For that data center upgrades and retrofits and new builds, because simply they extract more IT performance than air. They will allow you to lower the capital and operational cost, and also they help you to respond to climatic requirements and climate change. And the last point is that Zuta-Core lets you do that flexibly and not giving prescriptions, but rather engineering it into your own environment and your requirements. And with that, we conclude the call. So thank you very much all.
Thank you.
Thank you.
Yeah.